very much, Ricardo. I'm very happy to participate to this summer school. Thank you very much for the invitation. I'm also very happy to see virtually a lot of friends there. So thank you all for attending. So today I plan to talk about multigraded Sylvester Forms. So this is a work we did in collaboration with Marc Chardin from Paris and David Nemati, who was also at INRIA at that time. He's a former PhD student of Marc and did a postdoc with me at INRIA, and now he's in Sweden working for a company. This is a work that was motivated by solving of polynomial system. So what is the overall motivation? The overall motivation is to start from polynomial equations, f0, f1, fr equal to 0. You assume you have homogeneous polynomials, and you assume they define finitely many points. So the goal is to solve the system, that is to have a way to compute the roots, at least to be able to represent the roots. And so a classic way to do that is to build matrices. So we call that elimination matrices. And so those matrices are typically built by putting in their columns some coefficients of equations that vanish at the root. So this is the typical way to do. And so this is what we will investigate in this talk. Why we do that is because once we have these matrices, which is kind of an algebraic work that will change the form of the polynomial system, then we can extract the roots just by linear algebra methods. So this is what we have to keep in mind, that once we can put the problem into matrix form problem, then we can use linear algebra technique. So I will not speak about this third item, but I would like to mention how we can build those matrices. So the algebraic work that we can do on the polynomial system. So the goal of this work we did with Marc and Navid is actually to extend a family of matrices that is known in Pn. So there are a big family of matrices that is known over Pn, so the single graded case. And what we did is to extend that to the multigraded case. So this is what I would like to discuss today. I will start to review, actually, I will spend maybe half of the talk reviewing what is known over Pn, because the multigraded case is kind of technical, so it's better to have a good idea of what is done over Pn to see what are the new things or the obstructions we have in the multigraded case. So please don't hesitate to interrupt if you have questions during the talk.
Laurent, so, can you enlarge a little bit the screen? Can you enlarge the slide a little bit? Is that possible? Or is
this is what we try to do. Let me see.
Okay, this is probably maximum. No, this is worse.
Yes, this is worse. This is the best I can do by...
Okay, that's fine.
It's fine.
I have to be near the...
Yeah.
No,
is it okay like this or not?
Yes? Yeah, that's okay. Okay, I can.
Okay, sorry, Aaron. I cannot do best.
I can live with this.
Okay, and I have to do unit page. And okay. So let me start with a simple example that maybe you have all seen, is the classical case of two polynomials, f0, f1, in two variables, x0, x1, homogeneous. Okay, so you have two equations that are defined over P1, and you want to know if they have common roots, and if they have, how you compute those roots. So the classical tools here is the well-known Sylvester matrix. So from these two equations, f0, f1, you build the Sylvester matrix that you have probably all seen. It's a matrix with two blocks. The first block are the coefficients of f0, and the second block is built from the coefficients of f1. And the very nice property of this matrix is that the dimension of the co-kernel of this matrix is the degree of the GCD. That means that actually the co-kernel as a vector space as the dimension, the dimension of this co-kernel is the number of roots. So from linear algebra techniques, you can extract all the roots between f0 and f1 just from this matrix, because you have this formula that the dimension of the co-kernel is the degree of the GCD. Okay, so this is a very geometric property, actually. You keep the information of the number of roots. So if you think about what is the Sylvester matrix, the Sylvester matrix is actually a graded component of this map. So R is here the polynomial ring in two variables, x0, x1, over any field K, algebraically closed field, for instance. Then you consider this first map of the Kosul complex, which is just the multiplication by f0, f1. So this is graded. So here you have a shift by the degree of f0, and here you have a shift by the degree of f1. So you have this map. This map is graded, and so you can take a graded slice with respect to x0, x1. So you take it in degree d0 plus d1 minus 1, and then you get the Sylvester matrix, which is a matrix that lives in the coefficients of the f. And this is exactly how we build this classical Sylvester matrix. And it turns out that this matrix has this nice property that the corank of this map is exactly the number of roots. Okay, so now let me go to what we do over Pn, which is a sort of generalization of this. Yes, so sorry, I forgot to say that, of course, it's something very important to notice, that this construction is universal, in the sense that it only depends, I mean, if you change the coefficient of the FIs, you will build essentially the same matrix, because here you can put the coefficients of the FIs as variables, and then you get a universal matrix that you can specialize, and this specialization is exactly the same construction. Okay, so it's a universal construction, which is very important. Okay, so let me turn to Pn. So I start to put some more notations. So now I will take n plus 1 homogeneous polynomials in the variables x0, xn. So these are homogeneous variables of Pn. And now I consider, so there's homogeneous polynomials, capital Fi, that are here, and I assume they are all of degree di. Okay, so the notation I use is alpha for the monomials. So alpha is a multi-index, alpha 0 up to alpha n, and it denotes actually the monomial that you see here, x0 to alpha 0 up to xn to the alpha n. I will denote by this norm, this module of alpha, just the sum of the alpha. That's the degree of this monomial actually. And so the notation is here that the Fi is the sum of all the monomial x alpha in degree di, and I denote by ui alpha the coefficients of this monomial. So this is a kind of generic polynomial because I can consider this as a variable. Okay, so these are my notations. So we call A the ring where we put all the coefficients over Z. We call this ring the universal ring of coefficients. Okay, so this is the ring where lives all the coefficients of all the equations. Then we define by C the polynomial ring where you have all the coefficients and all the variables. And then I denote by I the ideal defined by the equations f0, fn, and by M the maximal ideal, the irrelevant ideal of Pn, that is the ideal generated by all the variables. Okay. So this is what I have just described is the generic case. And so then we can consider specialization. That is, we can give values to the coefficients ui alpha that you see here. Okay, so you can give values to an algebraically closed field that I call here K. And so each time I do that, I have a specialization. So it's a map that will specialize my capital F0, Fn that lives in this universal ring A of X to small f, that I denote this polynomial small f, and now the coefficients are in K. So these are polynomials in K of X. So the ui alpha here, I send to some specific value in K. I will denote by I of f, the ideal generated by the specialized equations. Okay. Okay, so the notations are set. So now I can tell you what is the generalization of the Sylvester matrix in this case. This is what we call the Macaulay-type matrices. It is built exactly in the same way. So instead of considering two polynomials, you consider n polynomials. You have this map, which is the graded map, the sum of C shifted by minus di that goes to C, and then you take a graded slice in degree nu. So here I have this shift in degree nu. So this is the polynomial ring in X, graded slice in degree nu, and here I have nu minus di because of the shift of minus di to define the map. So this is again the multiplication map by f0 up to fn, which is also called the first map of the Kosul complex. It sends this n plus 1 upper of polynomial g0 up to gn to the sum of gi fi. Okay, so if you look at this map, it only depends of the coefficients of the FIs. And so this is the usual generalization of the Sylvester matrix. And so we have this beautiful theorem, which was I think, as far as I know, proved by Lazare first, and then also appears in many papers of Joannolu during the period where he produced a lot of paper. So they prove the following thing that generalize the property of the Sylvester resultant. First, we define this kind of degree that we sometimes call the critical degree, which is delta. This is the sum for all the equations of di minus 1. So the sum for I equal to 0 to n of di minus 1. So we call that the critical degree. We call it like this because if you take any degree nu that is strictly bigger than delta, then you have the property we have seen before. That is, if I take now any specialized system, okay, I have the following. The matrix we have just built here that we call M nu, if you specialize it to the system you have, a small f, then this matrix is surjective if and only if you have no root over Pn. Okay, so this is the first property. And moreover, and this is probably the more important for applications in solving polynomial equations, if your system defines kappa roots containing multiplicities in Pn, then the dimension of the co-kernel is also equal to kappa. This is what is important here. So it's the same property as we said before for the Sylvester resultants, where we said that the dimension of the co-kernel is the degree of the GCD. So here we have the generalized version. The dimension of the co-kernel of this map is the number of roots of the system. Okay, so this is the property that is very, very important. If you take the case n equal 1, you can build the matrix in degree delta plus 1, you recover the Sylvester matrix. So if this is a square matrix, very well known. This is what we said at the beginning. Also, an important point to notice is that in general, this matrix is never square. Okay, it's not a square matrix, so there is a kind of miracle that in the case n equal 1, we have this matrix that is square, that is known as the Sylvester matrix. But in general, these matrices, they are not at all square matrices, so we use them. They have these properties, but we use them as non-square matrices to solve the polynomial system. So there are no determinants that are well defined from these matrices. Okay, so now I would like to give you some idea of the proof to explain why we need duality to prove this theorem. So I will give the main steps of the proof. So the first thing is that from construction, so let me come back here. So this is the map, okay? So what is the co-kernel of this map? This is C mod I, so the polynomial ring, mod the equations in degree nu, okay? So the dimension of the kernel is the dimension of this space. So for any nu, what you know is that the dimension of the co-kernel of this matrix is the Hilbert function of this quotient ring, k of x by I of f in degree nu. This is almost by definition. Okay, so if you want to have the property that this is equal to the number of roots, what you need to show is that actually this Hilbert function will reach the Hilbert polynomial, because since we assume that we have finitely many roots, we know that the Hilbert polynomial is a constant, and this constant is the number of roots. Okay, so how to prove that the Hilbert functions stabilizes to the Hilbert polynomial? We have a famous formula, the quadratic formula, that gives you the following thing, is that in this case, if you prove that the local cohomology of this quotient ring in degree nu, in degree 0 and 1 are equal to 0, then this implies exactly what you want, that the Hilbert function stabilizes to the Hilbert polynomial. Okay, so to prove our results, we only have to prove the vanishing of these two local cohomology modules. So how to do that? This is not so easy because you have specialized system. But since we have finitely many roots, we use this assumption a second time. We can actually bound when the local cohomology of this module vanishes from the generic case. So which means that if you prove that you have an integer nu such that this local cohomology vanish, so in the generic case, then you can prove that this will also vanish because we have finitely many roots. So this is a kind of a nice property, a property of fibers. Okay, so this is very useful because now to prove this assumption, it's easy because in the generic case, the ideal I is resolved by the Kosul complex. It's a complete intersection because you are in the generic situation. So to estimate the vanishing of this local cohomology, you can use the Kosul complex. So you can use the classical spectral sequences, and then you reach these two conditions. The first, the H0M local cohomology module, vanish exactly when nu is greater than this critical degree. So this is what we have in the theorem, actually. So you see that the bound is essentially given by the control of this module. And then if you look at the control of H1m, this is in degree a little smaller. Okay, so now the idea is, how can we get a better result than the previous theorem I showed? That is, can we work, for instance, in this smaller degree? So if we want to do that, we need to control, to have a vanishing of this term in smaller degree. So we cannot do we cannot do it for I. So the idea is to look at the saturation of I. Okay, so in order to improve this step here, we will look at the saturation of I. So what is the saturation? This is the quotient ideal of I by the ideal generated by all the variables. I quotient by n to the infinity. So this is also exactly ISAT mod I is exactly this module that we see here. This is ISAT mod I. So the question is, what can we say about ISAT in all the degree that are such H1m is already killed? So we want to modify actually the ideal I such that this is unchanged, because we will look at elements that are in the saturation. So this will be unchanged. But if we have a control on this term, then we can add element to I and try to lower the control of this term. Okay, this is done through the duality. So what is the duality in this case? So the goal of the duality here is to control ISAT with respect to I. So as we already noticed in the theorem, and actually you see here that H0m of C mod I is ISAT mod I. So when nu is greater of delta, this is equal to 0. So which means exactly that for all nu bigger than delta, then ISAT in degree nu is I. So you know exactly what is in ISAT. So what happens below? So this is a theorem that is due, I think, to Joanolu, 96, and also Shea and Storch, I think, independently. In 2001, there is a nice paper on that. And they prove the following. So now we look at what happens in between 0 and delta. They prove that actually you have an isomorphism of A modules. So I recall that A is the ring of coefficients of the FIs. You have this isomorphism that tells you that the graded component of ISAT mod I is controlled by the dual of C mod I in degree delta minus nu. Okay, so in some sense, you have another explanation of what is ISAT mod I. Okay, this map is not so explicit. You can make it explicit in some cases, and the cases that are known are the following. For instance, if you take nu equal to delta, you see that here you will get 0. So here you get A. So ISAT mod I in degree delta is isomorphic to A. So the question is, what is a generator as an A module of this component? We will see is the Jacobian determinant. I will do it in the next slide. Also, what we can observe is that for the condition we wanted to have, this nu greater than delta minus the minimum of I di, then the I is not generated in degree delta minus this degree nu, because you are below the minimum of di. So this is just the graded component of C. So in this degree, you see that ISAT mod I is just C, is isomorphic to C in degree delta minus nu. So it's a free A module. So this is very nice. And you can wonder, can we have an A basis? Can we produce an A basis of ISAT mod I in this degree? That is exact, whose number of generators should be exactly the number of monomials in degree delta minus nu. Okay, so this is what is known actually. So to get generators of ISAT mod I in degree nu for nu greater than that, okay, to do that, this is what we call Sylvester forms. So let me now recall the definitions of Sylvester forms. So we start from a multi-index gamma, which is denoted by gamma 0 up to gamma n, and we assume that this corresponds to a monomial that is of degree strictly less than the minimum of all the degree of the equations. Okay, so I still use this notation that the module of gamma is the sum of the gamma I. So assume that you have this for this gamma. Then we will make a decomposition of all the equations Fi. So I start from Fi, and I choose a decomposition where I put x0 to the gamma 0 plus 1, then a part of the polynomial Fi, plus x1 gamma 1 plus 1, a part of Fi1, and so on. So I choose a decomposition of Fi over these monomials, x0 gamma 0 plus 1, x1 gamma 1 plus 1, xn gamma n plus n. Why this is always possible? Because I have this assumption. Okay, I assume that the module of gamma is strictly less than the minimum of the degree of the di. So you can always do that. Of course, this is not unique. Okay, there are many choices for that. Once you make such choices of decomposition for all fi, you can build a matrix, a square matrix, because you have n plus 1 equations, fi, and here you have n plus 1 monomials. So you can build a matrix where you put, for instance, you put here in the first column, you put the decomposition of F0. Second column, you put the decomposition of F1. Last column, the decomposition of Fn. You take the determinant and you call this the Sylvester form in degree gamma. So the Sylvester form degree gamma is just the determinant of the coefficients of this decomposition. Okay. So if you look at the degree, this is not difficult. You can notice that Sylv gamma, the Sylvester form, is of degree delta minus the module of gamma. And moreover, it's not difficult to prove that actually it belongs to I sat. Okay, because if you multiply by any monomials here on the left, then you can play with the columns and you get here some FIs. So it's easy to prove that. And actually, this does not belong to I. So this is a true element in I sat in degree delta minus gamma. Okay, and of course, it depends on the decomposition when you see it like this. But what you can prove is that actually the class of the Sylvester forms in ISAT modi does not depend on the choice of decomposition. So this is truly an element that is well defined when you do it modi, because then this element does not depend on the choice of decomposition you did previously. So you see in my notation, I have capital S when it is in C, so it depends on the decomposition, and small s when I take the class modulo I, and then it becomes independent on the choice of decomposition. Okay, so for instance, we have these Sylvester forms, 0, 0. So what is it? Let me come back to the previous slide. You have gamma 0 equals 0, gamma 1 equals 0, gamma n equals 0. So you are just decomposing over x0, x1 up to xn. If you do that and you apply this, you have a sort of Jacobian determinant. We call it the twisted Jacobian because you don't use really the Euler formula, so you don't have the df that appears in the Euler formula. Okay, so this element, the Syl 0, which is almost a Jacobian, gives you an A basis of ISAT modi in degree delta. So you can generate all elements in degree delta in ISAT by this Syl 0, 0 element. Okay, and so moreover, what you have is that you have this duality that has been proved by Joanolu. If you take two gamma and gamma prime of the same degree, and still under the assumption that you can define Sylvester forms for these 2 degrees, then you have this pairing property that if you multiply the monomial defined by gamma prime with the Sylvester forms defined from gamma, then it is either 0 or the Jacobian determinant, the twisted Jacobian, if gamma is equal to gamma prime. So you see the pairing, if gamma prime is not equal to gamma, you get 0. If gamma prime is equal to gamma, then you get the generators of ISAT modi in degree delta. So this is a nice pairing, and this proves in particular that actually ISAT modi in degree nu for all nu in this delta minus minimum of IDI is generated by the set of Sylvester forms. So the Sylvester forms form an A basis of your ISAT modi in degree. Okay, so from there you can build new matrices. So they are known, they are called the hybrid elimination matrices. So what you do is just you start from the Macaulay matrices we had before, which correspond to this component. So this is the Macaulay component. You see I have this component. I take G0 up to Gn that I send to the sum of GIFI. So this is the first Macaulay block. Then the second block is due to the Sylvester form. So I will put all the Sylvester forms of degree delta minus nu by columns. So I have a column for each Sylvester forms of degree delta minus nu. So for each gamma, I have an A here, so just one column, and this column corresponds to the Sylvester forms of degree gamma. Okay, so you have matrices that is made of 2 blocks. The first block is the classical Macaulay style block that we have seen before, and then we have a new block where we put these Sylvester forms in the matrix. Okay, so 2 blocks like this. And so when you take nu greater or equal to delta, so the previous assumption we had before, there are no Sylvester forms in this degree because delta minus u become equal to 0. So there are none of them. So these constructions give you back to m nu. But if you are in degree, if you are in degree smaller than delta, but bigger than delta minus the minimum over I of the di, then you get new matrices that are smaller than the previous we considered. Okay, so what is the corollary of all this? The corollary is that we have similar matrices. That is, now the degree is this one, delta minus the minimum over I of di. And then if you take a specialized system, the matrix we built is surjective if and only if f has no root over Pn. And if f defines kappa roots counting multiplicity, then the dimension of the cokernel is kappa. So you can use these matrices for solving polynomial equations. So we have the same thing, that they are never square matrices, but they are more compact with respect to the Sylvester matrices, because have in mind that this integer here controls the number of rows. Okay, so it's much better if you can go below by minimum of the IDI in terms of the number of monomials. And also, if you think about the case, the classical case n equal 1, so 2 equations over P1, you recognize here not the Sylvester matrix, but what we call the hybrid Bezout matrices that are very well known. And they are kind of extension of the Sylvester matrix that are more compact. If you have met them before, I just wanted to say that they are encapsulated in this family of matrices over Pn. Okay, I will not go in this detail, but actually once you did that, you can go to overdetermined polynomial system. That is, you can take more equations than variables, and then you can still build this kind of matrices. We can prove that. But we don't have the duality and all these things, but we can prove that we can extend the property of these matrices. Okay, so I have finished with what exists over Pn. I would like to give a small illustration with rational curves, and then I will move to multigraded case. So the illustration I wanted to give to you is that I like very much is about rational curves. So you can consider a rational curve that goes from P1 to Pn. So it's just given by n+1 equations in two variables, homogeneous. And this defines the parameterization of the curve. So you assume that all the GI have the same degree D. And so what is the question here that is useful in practice is to compute the fibers of the map. So you give me a point on the curve, and you want to know how many, you want to know the preimages of this point. So you want to know how many x0, x1 corresponds to the inverse of your point by phi. Okay? So this is a typical application we would like to do. So the classical way to do that is to go to the graph. So you think about the graph of this map. So the graph lives in P1 cross Pn. And so you have a classical projection. So this map is just the projection on the second factor of P1 cross Pn to Pn. And of course, you map the graph to the curve. So through the graph, what you did is that you transfer this image just as an elimination problem, because the gamma lives in P1 cross Pn, and it maps to C just by elimination of x0, x1. You eliminate P1, so you just eliminate x0, x1. So you see here that we are in a, we transfer the problem of analyzing the image of a map to a problem of elimination of variables. And so to do that, to be able to do elimination, we need to know the equation of the graph. So in this case, this is quite classical because actually the blow-up is given by the symmetric algebra. And so it is essentially given by the CZGs of G0, G1, Gn. So the setting is the following. So you consider the Hilbert-Birch resolution of your equations, G0 up to Gn. So you have an Hilbert-Birch matrix here that I denote by psi. So this matrix is built with some columns that are of degree mu I. Okay, so this is given by the map. So you have to compute exactly the resolution to know what are the mu i's. They depend on the shape of the GIs. And so an important property of this Hilbert-Birch resolution is that the sum of the mu I is D. So what are the equations of gamma? They are exactly given by the column of this matrix that you multiply by T0 up to Tn. And those are, for me, the coordinates of Pn. So the coordinate of Pn, I denote them by T0 up to Tn. And so the equation of the graph are just T0 Tn product with all the columns of Psi. Okay, so I denote these equations F1 up to Fn. Okay, so the equation of gamma are F1 up to Fn. Okay, so if I sum up, the equation of gamma are equations Fi that are of degree mu I in x0, x1, and that are linear in the TIs. Okay, so they are linear in the TIs. Okay, so they are B homogeneous equations. So if I think about what I said before, the ring of coefficients is K of T0 Tn, so the variables of Pn, and what I want to eliminate is x0, x1. So I see my equation Fi as element in A of x0, x1 in degree mu I. Okay, so the first option is to build a classical Macaulay-type matrix. So if you do that, the critical degree you get is this one. The nu has to be greater or equal to the maximum of mu I plus mu j. If you do that, you can consider this matrix, which is just the multiplication by F1 Fn that you take in this degree nu. So for any nu that satisfies this assumption. If you do that, it's fine. You can compute this with this matrix, and you recover the nice property that the dimension of the cokernel of this map at a point P in C is the multiplicity of the point with respect to the curve. Okay, but you can do better with the Sylvester form. If you now consider the Sylvester form, you can go in this degree, mu I minus 2, so you can compare with this one. Okay, but now you don't exactly consider the matrix M, but the matrix H. That is, you have the multiplication by F1 Fn as before, but then you also add the Sylvester forms. Okay? So if you do that, you have a smaller matrix because you can go smaller in degree nu. You see that nu here gives you actually the number of rows of this matrix. And what we proved before is that actually this matrix has exactly the same property. That is, the dimension of the cokernel is the multiplicity. You have exactly this, is the multiplicity of the point. So you see that you gain a lot here by using the Sylvester forms. So the important remark is that actually, if you look at this matrix, it is made by linear form in the TIs. This is very classical. And what did the Sylvester forms is that they add some quadratic equations in the TIs in the matrix. So if you think about Riesz algebra, for instance, it gives you a quadratic equation of the Riesz algebra that appears in this list of equations. Whereas before it was only linear equations, so equation of the symmetric algebra. Okay, so I hope that everything was clear up to there. And so I would like to move to the multigraded setting. So how can we manage to build similar matrices in the multigraded setting? Okay, so I need to introduce a little more notations because now the equations will not be only homogeneous with respect to one set of equations, but R set of equations. So we have to have in mind that we will work over Pn1 times Pnr. So I need a set of equation xj for any j that goes from 1 to r. So xj is a set of variables of Pnj. And I will denote the variables by xj0 up to xjnj. So these are the coordinates of Pnj, of one projective space. So the ni's are the dimension of my projective spaces, and I will denote by n the dimension, the total dimension, that is the sum of the ni's. Yes, so that's it. And so once you have this, you can consider generic multi-homogeneous polynomials in this space. Okay, so you see we start to have more notations. So now the Fi will not be simply homogeneous with respect to one set of equations, but R set of equations. So you see here, it's homogeneous with respect to x1, x2, up to xr. Okay, and so I need a degree for all this set of equations, of all the sets of variables, sorry. So I will denote them by di, which is a multi-index. So di1 is the degree with respect to x1, and dir is the degree with respect to xr. Okay, and I will denote by di this multi-degree. So Fi is of multi-degree this di. Okay. Once we have this, then we can define the polynomial as before. That is, this is the sum of all monomials of this multi-degree di that are here, x1 alpha 1 up to x alpha r. and you denote by ui alpha 1 alpha r the coefficients in front of this monomial. So it's a similar notation as the one we used before. I will also call A the universal ring of coefficients. So this is the ring over Z where you put all the coefficients of the Fi. So this is very similar. I will denote by C the polynomial ring where you put the coefficients and the variables. By I, the ideal generated by F0, Fn. So this is the same. And now we need to replace the irrelevant ideal of Pn by the product of all the irrelevant ideals with respect to Pn1 up to Pnr. So this is the product of all irrelevant ideal of all the projective spaces. I will denote it by B. And similarly, we have specializations. So we specialize coefficients to an algebraically closed field. And similarly, we go from the generic equations, capital F, to the small equations. And not the small equations have coefficients in the algebraically closed field K. And again, similarly, I will denote by I of F, the specialized ideal. And my goal is the same, to produce matrices that have the property that when I do any specialization, the dimension of the co-kernel will be the number of roots. Okay, so as we have seen before, the strategy is actually to understand what we can guess about element in the saturation of I. So what are the elements that we can add to I and to which we have control so that we can lower the control of H0B of I. So what can we say about the saturation of I? So what is the saturation of I in this case? This is the saturation with respect to B. So remember, B is the product of all the irrelevant ideal of all the P and I. So this is what I will call ISAT from now. So with this, we will define, as we did before, a critical degree, this delta degree. So this delta degree is now a multi-degree because we have our projective space. So let's look at the component G, the component over P and G. So this, the component of the multi-degree with respect to P and G is supposed to be the sum of all the degree of all the equations with respect to P and G. So Dij, the sum over all the I with respect to P and J, minus this shift, which is the number of, which is actually the dimension of the projective space plus 1. Okay, before we add the sum of Di minus 1. Okay, so the minus 1 was I mean, this term was hidden in this sum because I took the sum of Di minus 1. So the minus 1 gives the n plus 1. So this is where we see this term here. Okay, and so now we have a multi-degree, delta 1 up to delta r. This is the sum of the multi-degree Di, minus the shift for any j. So this shift, which is here, n1 plus 1, n2 plus 2, and r plus 1. Okay, so this is the new definition of delta, which is now a multi-degree. And so the situation is actually not so nice with respect to Pn. That is, we don't have a theorem similar to what Joannolu proved, for instance. We don't have a true duality between ISAT mod I and the dual of C mod I for any degree between 0 and delta. We cannot do that. But we can say things outside some regions. So what are the regions here? What I call regions? They are regions with respect to the multi-degrees. That is, with respect to this sort of degrees. So we need to define two regions, gamma 0 and gamma 1. So there are two regions in the plane, I mean, in the set of degrees, of multi-degrees, that are given by this formula that corresponds to control of some modules, of some local cohomology modules of the Kosul complex. But I would like to say it, to illustrate it on an example. So let me consider this example to give you a hint of what are gamma 0 and gamma 1. There's two regions that we need to get out of what we are doing now. So here, for instance, this is the case of three generic forms of by degree 2, 2. Okay, so we are over P1 cross P1. So we take three forms, three B-quadratic equations in degree 2, 2 over P1 cross P1. If you look at delta, this will be 3 times because we have three equations, 2, 2 because this is their degree, minus the shift 2, which is 1 plus 1, and 1 plus 1 because we are over P1 and P1. So the delta is 4, 4. So you see in the picture, this is the point that is here. What is this picture? This is the degree with respect to the first P1, and this is the degree with respect to the second P1. Okay, and here you have a delta. So what we could expect is to have a duality in the sense that above delta, nothing happens. I mean, I sat mod I is equal to 0, and that's the end of the story. And below delta, we can have a duality. It's not the case. We cannot prove that. We have to remove actually some regions, and these are the gamma 0, gamma 1 regions. So the red regions that you see here, and the yellow regions, which is the gamma 1, so the red is gamma 0 and the yellow is the gamma 1. There's region we have to admit that we don't have a duality here. So there is no duality as simple as we stated before. So we have to focus in the white area. In the white area, there is a hope, but in the gamma 0 and gamma 1 region, there is no hope to have a nice duality as we had before. Okay, so the strict definitions is given by these technical definitions, but the idea is this, that you get this kind of area, gamma 0 and gamma 1, and these are regions that we will have to not consider for the duality. So here is the theorem we got. If you take a multi-degree, so if you think about the previous picture, a bi-degree, that is not in gamma 0 and union gamma 1, so that is not in the red and yellow regions, then you have the duality that we have seen before. Okay, so you have exactly that I sat mod I in this multi-degree mu is isomorphic to C mod I in delta minus mu. Okay, so if you are outside the red and the yellow regions, then you have duality. In the red and the yellow, you don't have it. You have something more complicated. We can say something about this, but it's not this kind of duality. So what are the consequences? For instance, you see that I sat mod I in degree nu is equal to 0 for all nu that are not in the lower square with respect to delta, union gamma 0, union gamma 1. So if I come back to the previous picture, that means that if you remove the yellow, the red, and this square here, that I can describe with my mouse, you see, this square here, as you remove it. So outside this square, then you have exactly that I sat mod I is equal to 0. So this is what we expected. And in this area, so which is, so if I come back again to the picture, this is the white area that is here. All the area that is here. For this area, you have the Macaulay-like matrices that we described before. We have the matrices mu that will hold because I sat mod I is equal to 0 in this degree. If you look at I sat mod I in degree delta, this duality will tell you also that you are isomorphic to A. This was one before by Catani, Dickenstein, and Stoffels. So you have again a multigraded Jacobian. I will describe it now in a few minutes, but you have a very similar situation. And so, yes, so I will do it now, sorry. So now I will describe this multigraded Jacobian that generate I sat mod I in degree delta. So let's do that. So it's a kind of similar decomposition, a little more technical, but very, very similar. So to not overload the notation, I will just describe it over two copies of projective space, Pn1 cross Pn2. And then for the rest, it's a very natural generalization. So how we proceed? We start by considering the variables of the first P1. So you see here, x10, x11, x1, n1. So these variables here are the variables of the first Pn1 component, so the first projective space. So you decompose Fi with respect to all these variables, and you choose some coefficients, Fi0, Fi1, Fi, n1 to the 1. Okay, so you can always do that, because Fi is homogeneous with respect to the first Pn1. So you can have many choices for doing that. Here we put a choice, but this is not very important. You can take any decomposition like this. Then what is important is once you did that, you look at these equations. So this one, the last term. So you make here a choice. You make a particular choice with respect to x1 and 1. You take this polynomial. This polynomial is homogeneous with respect to the second component, that is Pn2. And so these equations, you take it here, and you decompose it with respect to the second set of variables. So x2, 0, x2, 1, up to x2 and 2. Okay, so you make again a choice of decomposition. What you get in the end, if you summarize, you have decomposed Fi, your polynomial, with respect first to x1, 0. So you have these equations, x1 and 1, 1. So this is the first part here, where you stop right before this component. And then you have a decomposition of this fi n1 that you put here. So you see that the coefficients now is always multiplied by x1 and 1, x2, 0, x1 and 1, x2, 1, and x1 and 1, x2 and 2. So I hope this is clear how we do this decomposition. We first decompose with respect to the first Pn1. We take the last component and we decompose it with respect to the second projective space. Okay, and in the end, we get a decomposition like this. So why we do that? Because how many Fi do we have? We have n plus 1. And so here, how many components we have in this decomposition? You see n1 plus n2 plus 1. So again, n plus 1. So from there, we can build a square matrix. Okay, so this is what we do. D is the determinant of the matrix where each column is exactly the coefficients of each Fi with respect to this decomposition. Okay, very similar to what we did before. Once you have the choice of decomposition, you can make a determinant like this. And so this is a theorem that is due to students of Joanolu in 88, and also Katani, Dickenstein, Serfels. They proved that before. If you multiply this element D by this power of x1 and 1, this power here, then you have a generator of ISAT mod I in degree delta that is isomorphic to A. Okay, so this is what we call in this case the twisted Jacobian. The twisted Jacobian is x1 and 1 to n2 multiplied by D. This is the single element that generate ISAT mod I in degree delta. Okay, again, we have made a lot of choice in the decomposition before, but if you look at the class mod I in C mod I, then the element becomes independent of the choice of decomposition. So it gives you a canonical generators of ISAT mod I in degree delta. Okay, so you see that the decomposition we did, we can actually extend them in the same ID as Sylvester forms we define over Pn. That is, instead of decomposing with respect to the variables, we will put some powers on the variables. So here, for instance, we take a multi-index alpha, that is a multi-index with respect to the first Pn1. So then we assume that we have these conditions. I would like to remind you that this is the conditions we used over Pn to define the Sylvester forms. So then I do that here exactly over Pn1. So I choose an alpha multi-index and I put this condition. And then I do the same. I take a multi-index with respect to the second Pn2. And of course, I put this condition as well. Okay, so how do I manage to define the Sylvester forms here? In a very similar way, I define the polynomial Fi as follows. First, I decompose with respect to the first set of variables of Pn1 with the multi-index alpha. So x1, 0, alpha 0 plus 1, up to x1, n1 minus 1, to this power plus 1. Okay, so I just add some powers. And then the last term that remains here, I will decompose it. It is here in the parentheses. I will decompose it with respect to Pn2 and this multi-index beta. So you see here the decomposition, x2, 0, beta 0 plus 1, a component here, and so on. Okay, so we do exactly the same as for the twisted Jacobian, but we put some powers. If you do that, you can do exactly the same. You define a determinant in this in a very similar way. And so this determinant now depends on alpha and beta. So for any choice of alpha and beta, we make this kind of decomposition, and so we get this determinant that we call d alpha beta. Okay, and so the definition is that for any alpha and beta that satisfy to these two important conditions here, that are just the conditions to be able to define the decomposition I described before, then we call the Sylvester forms of alpha beta of by degree alpha beta. Just the element d alpha beta multiplied again by this monomial here. Okay, so it's very similar. You can define Sylvester form as a sort of determinant that comes from a decomposition of DFI. Okay, again, you can prove that mod I, so the class of this element in C mod I, is independent on the choice of decomposition. So this is very important, and you get some canonical elements associated to DFIs for any by degree alpha beta. So I will do that here with a small s. Okay. Okay, so if you look from the definition at two-phase elements, what you can observe is that actually all the Sylvester forms in alpha beta, first their degree is delta minus this by degree alpha beta, okay, and moreover it belongs to ISAT. This is not difficult at all to prove. Okay, so you have kind of natural elements in ISAT modi degree delta minus alpha beta. Okay, but if you have in mind that the duality that I mentioned before, the duality proved essentially that ISAT modi in this degree delta minus alpha beta is isomorphic to C, the polynomial ring, in this by degree alpha beta. So how many elements you expect here? So what you get is that this is a free A module, and the rank of this free A module is the number of polynomials of degree module of alpha, module of beta. But look at this, how many Sylvester forms we have? Exactly this dimension, because for any alpha beta, for any choice of monomial alpha beta, you can build the Sylvester forms. Okay, so what we have here, we have this isomorphism, we know the dimension of this space, and we have good candidates to be an A basis. And so this is what we proved. We proved that we have this sort of pairing that is very similar to what we have over Pn. So if we take a list alpha 1 alpha r of multi-index and a list beta 1 beta of multi-indices, you assume that the modulo of alpha I is the modulo of beta I. Then you have in the same idea that if you multiply the Sylvester forms alpha 1 alpha r with a monomial xi beta I, then you get either 0 if this degree is different from the degree of the beta i's, or if it is the same, you get exactly the twisted Jacobian. So it's the same pairing as before. Either you get 0 if the two lists of monomials are different, either you get exactly the twisted Jacobian if they are equal. So you have a pairing. And so this means that actually, this is what we proved. You can prove that for any degree mu j, that is in between 0 and the minimum of the dij, then all the Sylvester forms in this degree, mu I, gives you a basis of ISAT modi in degree delta minus mu. Okay, so this is what we wanted to prove. For all this, in these conditions here, so if the mu j are all smaller than the minimum over I of dij, then the Sylvester forms gives you exactly an A basis of ISAT modi in degree delta minus mu. Okay, so this is the generalization we can do from the duality over Pn to a product of Pni up to Pnr. So we don't have a full duality in this multigraded case, but still we can prove that the Sylvester forms generalizes. So you have the property that a part of the saturation, ISAT modi, can be generated by those Sylvester forms once you can describe them. So now I'm just giving some consequences, so the hybrid elimination matrices. So we can, as we can expect from what I said before, if you take a degree nu, that is delta, so the critical degree minus this index, mu1 up to mu r, and you assume the conditions we put for the Sylvester forms, then you can improve the Macaulay-type matrices by adding Sylvester forms. So what is it? This is what we did before, the matrix H nu. So you have the Macaulay style component here that takes G0, Gn to the sum of GIFI. And then you add to this matrix columns that corresponds to all the Sylvester forms of degree delta j minus mu j. Okay, so the alpha must be such that the modulo of alpha j is delta j minus mu j. So in summary, you put all the Sylvester forms of the expected degree here. Okay, and once you do that, you get a new elimination matrix that have a first block of Macaulay type, which was the classical construction, and then you add those Sylvester forms, and then you have two blocks, and then you see that if nu is not in the zone that I described before, that is delta minus n to the r union the red and the yellow regions gamma 0 and gamma 1, then this H nu is purely the Macaulay, so you don't have Sylvester forms. But if you have in this degree, so you see here the gain, minimum of I dir1, minimum of I dir. If you remove this, you still have an elimination matrices that has the expected property. So what we gain is exactly to be able to push this minus, the term minus this, to the classical Macaulay construction. Okay, and if you do some specialization, so this is the natural goal we had at the beginning. If you take a specialized system of multi-homogeneous equations, and then you take a degree nu, delta minus this minimum of di, then you have the expected property that this matrix is surjective if and only if you have no root. And if F defines kappa roots, then the dimension of the co-kernel is kappa. Okay, so the properties of these matrices extends. And moreover, we can also discuss, I will not discuss that, but you can also go to the overdetermined multi-homogeneous system. So you can have more equations than the number of variables. You cannot prove the duality results, of course, but you can prove that this kind of constructions gives you this property that the dimension of the co-kernel is the number of roots. Okay, so to conclude, this is my last slide. I would like to discuss one of the motivation we had at the beginning with Mark and David, that was to understand the Dixon elimination matrices. So these matrices was given by Dixon in 1909 without any proof, just a claim that it works, and these are very nice matrices. And so they are elimination matrices in the following setting. You are over P1 cos P1, okay? And you consider 3 generic equations of the same by degree dE, okay? So you take 3 equations of the same by degree over P1 cos P1, okay? So if you look at this case, the delta number will be here 3D minus 2, 3E minus 2, okay? Because I do 3 times dE minus 2, because P1 and P1 gives me a shift by 2 and 2. So this is delta, which is the dot here, you see here. So what you can prove is that actually outside the yellow and the gray regions, okay, this is what we discussed before, the duality tells you that I sat mod I is equal to 0. Okay, so in the white zone, I sat mod I is equal to 0. So the Macaulay matrices that I denote here by M nu exist and gives you the and have the expected properties. So this was well known and this was fine. What happens is actually Dixon gives these matrices that I put gave matrices that I put in the red lines here that you see here. There are matrices on these lines. And what we actually prove is that in this pink area, you have the Sylvester form. So in this pink area, the duality tells you that I sat mod I is a free A module, and it is generated by the Sylvester forms. And the funny thing is that the hybrid matrices H nu we can build for this matrices from the Sylvester forms gives you exactly the Dixon matrices that are here. So the Dixon matrices enters this family H nu, and they are actually at the borders of this family. Why Dixon described these matrices is because there is a kind of miracle of numbers that these matrices are square. So this is very rare, but if you count the number of columns that appear here, it's exactly the number of rows. So this is very rare, but this happens in this case. And so this is why Dixon looks at these matrices, because they are square. But they are now explained by these duality results that actually in all this pink area, I sat mod I is a free A module and is generated by the Sylvester forms. Okay, I will stop here, and I thank you for your attention. And I apologize for all the notations I had to add to the talk.